Okie dokie, we'll go ahead and get started. Today we're gonna do more about understanding the numbers. And then next week in our 2 days before fall break, we're gonna do a little bit more about numbers and what they tell us and what they don't. Yeah, and then next Wednesday, so on what is that, 5 days from now? I will have exam 2 to hand out for y'all to do either over fall break or when you get back from fall break, because it'll be due a week later. Alrighty, I'm gonna go ahead and hide the Zoom captions. Folks who are on Zoom, feel free to keep using those, but I am gonna go ahead and use the Google ones. Alrighty, and I just realized I dove into this and I have a link to show you. So real quick. And I will throw the Zoom captions back on for people who might have an issue with this. Okay. So this is a link we had been talking about, correlation being not causation. And this is a link that shows some examples of how people thought certain things were causal when perhaps they weren't. So from intro, or if you've ever taken industrial organizational psych with Dr. Jackson, you may have heard about the Hawthorne effect. And so basically researchers were studying worker productivity. So they tried to do things like change the level of light so they may make it brighter or dimmer. and or make it more tidy or move stuff around. So they were like, whoa, some of this is really making a difference. And then they noticed when the researchers left, even if they left those changes in place, productivity went down. And so basically what they discovered is that the people worked better, not because of the lighting conditions, not because they tidied the workstations, but because they were being studied and they were interested in that. And they thought, ooh, someone cares about us, right? So that can be part of it as well. We've talked a couple different times about, sort of the gambler's fallacy, so I'll skip that one. The sports equivalent of that is the hot hand. And this is the idea that like when you get into a role in sports, like you should keep giving it to the person who's doing well, right? And like sometimes that person, yeah, is just like in the zone that day, but like the hot hand is not actually a thing. And this kind of relates to superstitions we were talking about with pitchers and catchers. There's this NHL player who used to dunk his hockey stick in the toilet because he thought that would break his streak. Would not want to be the person who got high sticked by him after that, right? All kinds of fun things. This one is about hormone replacement therapy. So women who enter menopause are often prescribed hormone replacement therapy. And in the 90s, this was like the thing. It's like, oh, you're going into menopause, get on HRT. But basically what they found is that women who use, it's like a lot of the health statistics we find, women who are able to access a doctor and get a prescription for HRT and consistently get that prescription, they are more likely to be wealthy or at least upper middle class, right? So it wasn't that hormone replacement therapy itself was giving people a health boost in general. It was that essentially, if you're able to afford hormone replacement therapy, you are also able to afford a host of other medical treatments, preventative care, things along those lines. This kind of reminds me of what happens with the stock market in general. So someone just sort of joked that was like, oh, the Super Bowl outcome could predict the stock market. And people were like freaking out about it, right? This is a spurious correlation, but also we know that the stock market is really susceptible. So I don't know if y'all remember when Twitter first started letting people buy the blue check mark. I'm gonna always call it Twitter, it's not X. And anyone could buy it and then make their account look like whoever. And someone bought one and made their account look like one of the major pharmaceutical companies that sells insulin. Insulin is way jacked up. They profit off it a lot, which is really sad because it is a life-sustaining medication, right, for people who are diabetic. And so they posted, hey, we're gonna make it either like more affordable or free to people. And investors sold all their stocks in that company, and that company's stock crashed. So we know the stock market is vulnerable. A couple other examples here. Minimum wage. So basically, some people say that a higher minimum wage hurts businesses. We've certainly been hearing that quite a bit lately, right? And in fact, there's no evidence from this claim. And so, I mean, the fact that the federal minimum wage, $7.55 an hour, is still less than what I made as a cashier at Kohl's in the year 2000, right, is horrifying, right? The fact that we have not raised the minimum wage in years and years and years. Literary critic George Shaw once quipped, if all the economists were laid end to end, they'd never reach a conclusion. essentially, like, people are always going to make arguments like, is this a thing? Is this not a thing? But basically, economic projections suggest that most of the companies that would be paying a higher minimum wage can definitely afford to do so, right? They're giving their CEOs and their stockholders huge bonuses every year, right? And there's these ideas that if you eat breakfast, that makes you lose weight. There's a whole lot of other stuff going on there, right? And that maybe if you're at a family dinner, and this was a big thing again in like the 90s and 2000s, it's like, eat dinner with your family, and that will prevent all kinds of bad things from happening. And again, it's not taking into account the fact that like some of these families have the luxury of being able to eat together because the parents aren't working 3 jobs and things like that. So for example, this is another one where the statistics can be misleading. So men do die more often by suicide than do women. Women do choose different means sometimes that are not as lethal. But there's a lot of confounding factors, and people have been like, oh, it's being a man and that's what causes it. No, because women actually attempt suicide at higher rates, so it's much more complex. Oh, and then of course our favorite, the vaccinations, right? And again, like this having ramifications of people not getting themselves vaccinated, not getting their kids vaccinated because of, again, this one study by Andrew Wakefield, that the whole goal of it was really to be able to promote his own version of the vaccine, right? So I just liked that article because it gave you some really nice examples of these correlation things that people have said are causal. And this, again, you turn on the news, you turn on Good Morning America or Today, you're going to see these types of things reported every day. And so then how and why and when can we say causality actually exists? Well, the big thing is when we run an experiment. Now, we can run an experiment and do a crappy job. And that has happened throughout history of psychology. Or there could just be other stuff that messes with our experiments and they end up having to either toss data or they're not very good. So for example, a colleague of mine was running a study here and with another colleague at a different university, and they found out halfway through running the study that there was construction at the other university right outside the window of the room where they were doing memory tests. Yeah, they had to check all that data, right? So you're going to try to control as much as you can in an experiment so that you can try to say, this is actually what's causing that. So using that random assignment is a good piece of that. A lot of folks back in the day, and some people still do this, it was just literally flipping a coin. Oh, you got heads, you're in this group. You got tails, you're in that group. Or drawing a group out of a hat, so the group number usually. Nowadays, a lot of people use what's called random.org. It's a random number generator, and it can do the same tasks, but via the computer. And then longitudinal studies, I've mentioned before, the hierarchy kind of puts these lower than I think they should be, to be perfectly honest, because with longitudinal studies, we're able to establish not only a potential causal relationship, but a timeline, right? So longitudinal studies in the area of eating disorders are the ones that establish that, like, if you have more internalization of the ideal you're supposed to look like at, let's say, 10 or 12, that is highly linked to having body dissatisfaction and developing an eating disorder at subsequent ages, right? And so these are things we can't randomly assign in the lab, but can give us really important ideas about risk factors that can help us to design effective prevention programs. And so one of the most effective body image eating disorder prevention programs It's called the Body Project, and it's based off a lot of that data. So it really focuses in on the appearance ideal and how do we combat that. So your book also talks about something called regression to the mean. Regression is just a fancy way of statistically looking at more than two variables and how they relate, basically. So correlation, you can only look at how two variables relate. With the regression model, you can look at multiple variables and how they might be related to each other. But it's based on the same type of analyses as correlations. Regression to the mean is that extreme scores tend to be followed by scores closer to the mean. And this is a pattern we see in a lot of different types of data. So I have a video about this.
Which is most effective for helping people learn? Punishment or reward? We'll consider the case of Israeli fighter pilot training, because instructors there found that negative feedback was far superior to positive feedback. If a cadet performed a particularly poor maneuver, they would reprimand him, but they noticed that on follow-up attempts, his performance invariably improved. In contrast, if they praised a cadet for executing a skillful maneuver, his performance on subsequent attempts typically declined. So naturally, they concluded that positive feedback is ineffective or even detrimental, whereas negative feedback is what works. The problem is, this seems to contradict a body of research that shows positive feedback is actually more effective than negative feedback. For example, in studies involving teachers, it was found that if a teacher increases the ratio of positive feedback to negative feedback, that actually increases the percentage of time students spend on task. In another study, rugby players were given a video feedback session following a game. Except half of them were shown their highlights and they were praised for what they had done, and the other half were shown their biggest blunders, their mistakes, and they were scolded for doing things incorrectly. Now, a week later at the next game, it was the players who had received the positive reinforcement who performed the best. And in fact,
one thing I should say is this is based on years of research on learning. And in particular, we know from research with animal training that positive reward is so much more effective than punishment, for example.
The difference was not just psychological. Blood tests revealed that the players who received positive feedback actually had higher levels of testosterone than players who had received the negative feedback. I think that's quite remarkable, that even a week post-feedback, you could still see a physiological difference between the two types of feedback. Wow. Well, so why didn't this work for the Israeli fighter pilots? Well, maybe there are cultural differences, and in some cultures negative feedback works better. Or maybe it's task dependent. Perhaps some skills, like learning to fly a fighter jet, require more negative feedback. Or maybe the feedback had nothing to do with the performance of the fighter pilots at all. Maybe they would have performed in the same way regardless of the feedback they received. Go with me on this. Imagine you have 100 students taking a test which consists of 100 true or false questions on a subject they know nothing about. Now, assuming they all answer randomly, we know that the resulting distribution of scores will have an average of around 50. But just by chance, some students will have scored significantly better or worse than the average. Man. If you select the top 10 students whose scores were all above 50 and gave them a second very similar test, you would find that the average of their scores would drop back to around 50. Similarly, if you selected the bottom 10 students, their score on a subsequent test would rise to 50. This is just regression to the mean. Regression to the mean is the reason why if you have a really good round of golf today, your round tomorrow will not be as good. Yes! That is because random chance plays a role in virtually everything that we do. So the outcomes of events are influenced by both our skill and a little bit of luck. So if you have especially good luck on one day, chances are your level of luck will not be as good the next day. Now that sounds a little bit like the gambler's fallacy, which states that past events influence future probabilities. For example, if you flip a coin and it comes up tails a couple times, the gambler's fallacy is to expect the probability of heads to increase for the next flip. In reality, it doesn't. It's still 50-50. The idea with the gambler's fallacy is that probabilities change so that overall things even out in the long run. That's the idea. With regression to the mean, it's not that things are evening out. It's just that extreme events are becoming diluted by the average events, which happen much more commonly. Now with these students, they were completely guessing on every question. But even when you know something about the subject, there's still going to be that element of chance. And so regression to the mean always occurs, just to a lesser extent. This is really important to consider in research. Imagine you're trialing a new drug to help prevent heart disease. So from a sample of patients, you select those in the bottom 10% of heart health indicators, people with high blood pressure, high cholesterol, that sort of thing. Now, after a month of being on the drug, you test them again to find that their scores have improved. Well, great, the drug is working, right? Well, maybe not. See, the trouble is that although blood pressure and cholesterol are more stable than, say, your score on a random true or false test, there is still some inherent variability caused by, say, your level of stress on the day, or your recent diet, or even the uncertainties introduced by the measuring apparatus. So the people who ended up in the bottom 10% on the first test likely had these factors all count against them. They were particularly unlucky. But you should not expect them to be as unlucky when you test them a second time. So their scores should improve just based on random chance. That is why it is so important that clinical trials use control groups drawn from exactly the same population so that you can see whether the drug improves scores more than random chance alone would. Or what about assessing the...
And that's why random assignment and placebos are so important in doing these types of drug trials, so that you can account for the fact that, like, we know psychologically, if you take a medication and you're told it's going to help you, not only does that affect you mentally, but we know that there's a mind-body connection, and like physically you can get better just because someone told you you're going to get better, basically. So that's why it's really important to see, does the medication actually help you improve over and above that?
Impact of speed cameras. When they're first installed, they're normally put in locations that have had a high volume of accidents in the previous year or two. Makes sense? Now, those accidents are likely due at least in part to bad road design, but also due at least in part to bad luck. And so you shouldn't be surprised that after a speed camera is installed, the number of accidents goes down. It would go down anyway, simply due to regression to the mean. Meanwhile, somewhere else that previously had a small number of accidents will likely have more. So the overall accident rate may not change, and yet we will feel as though our investment in road safety has paid off. But perhaps what's most troubling about regression to the mean is how it influences our perception of feedback. For example, with the fighter pilots, after they execute a maneuver particularly poorly, chances are the next attempt is going to be better, regardless of the feedback they receive. Similarly, after an especially successful display, chances are the next attempt is not going to be as good. And that has nothing to do with the feedback and everything to do with the statistical nature of our universe. But we are hardwired to see patterns and causality everywhere, which is why the instructors felt that positive feedback was detrimental and negative feedback is what works. And this is really unfortunate because that is the exact opposite of what well-controlled psychological studies show. You know, I think it's really unfortunate that if you give negative feedback, chances are you'll be rewarded. They will do better. And if you give positive feedback, chances are you'll be disappointed because it's difficult to maintain that level of luck. But that's the way our world is. So think about that next time before you tell someone off. If you stay positive, it may just work out for the best in the long run.
So again, the whole idea that, like, just because of error and randomness, stuff can look different when it's really not. This goes back to that type 1 and type 2 error, right? So we want to make sure that we are really paying attention to these things. So one of the things that can happen when people are reporting statistics in especially popular media is that they will try to create eye-catching graphics, which is great, except they're not always done well. Sometimes we have what's called chart junk, which is unnecessary or distracting elements of a chart or graph, or just like a whole bunch of stuff on there that doesn't need to be there. Another thing that can be misleading is looking at the axes. So sometimes it's the axis, you'll think like, oh, that's 0, that's 20. But in fact, the axis has been stretched to make the difference look bigger. So in fact, the bottom is 10 and then 20, right? The other thing we need to look at is, do the numbers add up to 100% if they're using percentages? And this is perhaps the worst example of that I've ever seen. So if you just take a minute to mentally, sort of think about adding those numbers up, right? It's gonna be much higher than 100%. And yet they put them in this diagram of a person, again, eye-catching graphic, right? Suggesting that they are parts of a whole that would add up to 100, right? Like 61% here, 78% there. And just by the nature of these statistics, right? We know that there's gonna be overlap on these things, so portraying them as distinct is misleading. And problematic, because it ignores the nuances of people being more than one thing, right? So this is, egregious. But you can also see this in published studies. So like I was just mentioning, you can take the same data and by looking at the x-axis and stretching or compressing that, you can get different. So these are the same data. This here, the x-axis is set at 0. Here it's set at 2.6. Right, so if you narrow in on those differences, they look much bigger than when you look at it here. You can still see there's a difference, right? But it's not as dramatic as when we do this. Same thing over here. Here we have the axis at 0, right? Looks pretty flat, but again, if we stretch it, and you'll often see these sort of double hash marks when people do that, indicating that they've jumped to a number, then it looks much more dramatic. And now it's entirely possible that differences this small, depending on your sample size and what measure you're using, can be statistically significant, right? But a lot of academics will do this to make them look more dramatic. I think I've done this in a publication, right? And it's silly, but it helps you get published. Because reviewers don't always think of things in this way, right? We also need to think about time frames, right? Sometimes people will be like, oh, this dramatically increased. It's like, since when, right? So we need to be thinking about that. So what time do people narrow in on when they're discussing the frequency of something happening? So I believe if I'm recalling, this is from this is my alma mater's weekly newspaper put out by the students. And they were looking at COVID cases after people came back to campus. Right, and so before people got there, right, there's a little bit of a, and then it goes right up, right? But we're only looking to there. We haven't looked at, what happened after that. And I think it's partially because that's when they were writing the story, right? But it's really interesting to think about, what are the implications for that time span that you look at, right? It'd be really interesting to see what about the previous year? How high did the cases get, right? Because it's saying the college is reporting their highest number of cases, but like how much higher is it than previous times? So what are the numbers you'll encounter as you read journal articles or even popular press stuff? So the mean, which is just the arithmetic average, literally to get a mean, you just add up all the numbers and divide by the number of people you have. The median is the middlemost number. And then one thing I realized that's not on here is the mode. And the mode is the number that occurs most frequently. A lot of times when we look at data, we will see outliers. And these are data points at the extremes that are going to differ from most or all of the other scores. They can skew our data. Typically, we're looking at 2 or 3 standard deviations above or below the mean. Sometimes we take these folks out because sometimes we look at their scores and we realize, like, They just must have had an error when they put stuff in, right? So, for example, there have been times in the past where I collect data on people's height and weights for my eating disorder studies. And I'm doing it internationally on a website, and I'll tell them to do it in feet and inches. And then their weight in pounds. Like if they're from the UK, they'll enter it in stone. I think a stone is 14 pounds, right? So they might be like, I'm 6 stone or whatever. And but if you put in 6 as if it were pounds, you're gonna get like a dramatically low body mass index if you calculate it, right? So sometimes we throw those people out just because we know this is an error. So the standard deviation itself is a measure of variability. This is the formula for it. It's basically the square of the distance from the mean of each person's score. And then you find the average of that and take the square root. To be perfectly honest, I do not know who originally developed this formula. I'm assuming some genius mathematician. But this isn't clearly the only way to study variability, right? Just what someone came up with and we've kind of rolled with over the years, right? You can also measure variability by just looking at the range of scores you have, right? Or the distribution of scores, like on a scatter plot. So how can you avoid being scared by numbers, right? We don't want you to be scared by numbers. We don't want you to feel like you can't interpret them. Well, one of the things that we can look at and that we look at quite a bit is probability. And probability is the likelihood that a particular event will occur. That's often expressed mathematically, with 1 indicating certainty that the event will occur, or -1. Put that out there. And 0 indicating certainty that it will not occur. And so what I have now are a few different videos that talk about the use of statistics in psychology. And one of the things I really made a concerted effort to do when I created this class is not to just find videos about stats from old white guys, although the next one will be an old white guy, but try to find more diverse voices talking about stats.
Hello, I'm Dr. Keon West from the Institute of Psychological Sciences at the University of Leeds, and I'm here to talk to you about the importance of statistics. It's very rare that statistics happens to be anyone's favorite part of studying psychology, or any other science for that matter. Statistics can be complicated, they can be confusing, they can be difficult, and often they're just not that interesting, at least not for many of our students. But statistics are still very important. And I'm going to try and explain to you why they're very important and why they're in fact essential to conducting this kind of scientific investigation. Suppose you had a question. Any kind of question would do. Let's say that you wanted to know whether or not men were taller than women. How would you go about figuring that out? Now, the immediate thing would be to say, well, I could go out and measure the height of a man and then measure the height of a woman and see if the man is taller than the woman. And if that works, then you could say that men are taller than women, right? Well, no, wrong. Because there's many reasons why that's a very bad way of handling it. You could measure a particularly tall man and a particularly short woman. So you could, in this instance, find that one man is taller than one woman. But if you had measured 2 other randomly selected people, it's possible that you would have found that the woman was taller than the man. And then you'd have a different result. Okay, then you'd say, what do we do in this case? Maybe we should measure multiple people. You could go around measuring groups of men and groups of women, and then you could compare them. But how would you do that? Would you tick a box every time a man was taller than a woman and tick another every time a woman was taller than a man? And then I guarantee you, even if you went through a very rigorous system of measuring people, if you gather any 2 groups of people together, even randomly selected, you will find that their heights are different, because human beings vary in height. And so what you need to know is this difference in height a real difference, or just an illusory random difference that happens to crop up? Let's say you had another question. Do students who study more do better at exams? We're not assuming any direction. We're just looking. Do students who study more do better at exams? How would you check that? You could find one student and you could say, well, this student, she studies very hard, but she doesn't do particularly well. And maybe you find another random student and he studies very little, but he does very well at his exams. Should you then conclude that, well, clearly studying actually doesn't do much for your exams or doesn't make much of a difference? Well, of course you can't. Because if you had selected two other students quite at random, then you might have found that actually this student studies very little and does very poorly. And the other student, why, she studies a lot and does very well. But even then, we're not sure. We can't tell if this is random or if it's fluctuating or if it's a real thing that actually is emerging from the data. You could measure a bunch of people, a number of students, but how many would be enough? And how much of a relationship would be enough? You could plot them on a graph, as I've done, and you would see that the students are moving from those who study very little and get very bad grades to those who study very much and get very good grades.
So what he just showed, and I'll back it up a couple of seconds, this is a scatter plot, basically. Normally you would just have a dot where each person sees, making it visual. But this is one of the ways we can look at our data to see sort of the direction it's going.
The students are moving from those who study very little and get very bad grades to those who study very much and get very good grades. So it looks like something is going on. But at what point can we declare that, yes, we've decided this is a real relationship and not just something that looks like a relationship? I'll ask you two more questions that are a bit more complicated and not as easily visually represented. One would be, how would you check whether exercise predicted exam results? This is not just whether there's a relationship between exercising and getting good grades. This is whether one variable predicts the other or explains the variance in the other.
So he's talking about the difference between correlation and causation here.
Or an even more complicated question, what if you wanted to know how exercising and going to parties influence exam results together? That's a bit of a tricky one to visualize, because it could just be that exercise predicts better grades and partying predicts better grades. Or they could interact with each other in some way, so that one predicts more, one predicts less, and that they balance each other out in some places and actually make each other stronger in other places. This is a very complicated question, and it's not that straightforward to get it into our heads, and it's definitely not that straightforward to check by simply putting data points on a graph. So if you have all these questions, you have some very specific questions about the data that you need to have answered before you can decide whether or not any of these relationships are real and whether or not any of these relationships are meaningful. You have questions like, how many data points do you need? At what point do you stop thinking it's just a fluke or random fluctuation and decide that it's an actual, stable difference that's emerging in the data? And how can you measure whether or not relationships between variables are strong or weak, and whether they go in one direction or in another direction? And if you understand the importance of getting these answers from the data, then you've understood the importance of statistics. Because statistics is how we answer these questions. Statistics allow us to decide whether measured differences are meaningful, or whether they're just due to chance or the way we measured it. Statistics help us to decide whether relationships are real, or whether these relationships are just illusory. They help us decide whether one variable predicts another, or whether it's smarter to say that the relationship goes in the other direction. And they also help us decide how multiple variables predict each other at once. This gets increasingly complicated as you go up the levels, but I will run through two examples to help us understand what we're doing with statistics and how psychologists in particular choose which relationships to look at and which ones to decide were just due to chance. So let's go back to our original question. Are men generally taller than women? We know that not all men are taller than all women. We know that some women are taller than some men. But we can measure overall the height of men and women. The way that we do this is probably something you would recognize from taking classes earlier in high school or at A-levels. You'd calculate the mean of the height of the men and the height of the women. That's incredibly straightforward. To get the mean height of men, you simply add together all the heights of the men, and you divide it by the number of men that you counted. To do the same thing with the women, to get the mean for the women's height, you add together all of the heights of the women, divide that by the number of women that you measured. Now that's very straightforward. But as I said earlier, if you get any two random groups of people, even if both of these groups are composed of men or both are composed of women, there will be a difference in their heights because of the normal fluctuations. So there will be a difference in the means as well. How then do you decide whether this difference in means is a meaningful difference in the means? To do that, because we're taking two independent samples, psychologists would probably use an independent samples t-test. This is a test specifically designed to test whether means are different between independent groups, two independent groups. You can see the formula for the t-test.
And independent groups here just means people in one group couldn't be in the other group. So gender is a simple way to look at it, right? Men versus women, but like in an experiment, it would be they were randomly assigned to one group or the other, so they couldn't be in the other group.
On the slide. It involves subtracting the mean height of one from the mean height of the other. So in this case, we could say hypothetically, subtract the mean height of the men from the mean height of the women, or subtract the mean height of the women from the mean height of the men. And then you put all of that over the standard deviation of the two groups. Now, why measure the standard deviation? What is it? The standard deviation is a measurement of how much these heights vary around the mean. So it's a measurement of the variance within the groups. And you always divide the variance between the groups, which is what we have on the top, with the variance within the groups, which is what we have on the bottom. And in general, if you find that the variance between the groups is large and the variance within the groups is small, then you say that you have a meaningful difference. But we're still not done. We have a t-value, and that's a good value. Now we have a good idea of whether or not this variance means something, but we still don't have a cutoff point. We still have no way of deciding this much is significant for us and this much is not significant for us. This much we'll ignore. Psychologists have chosen a point, and in order to get to that point, you need to calculate the p-value, or to find the p-value. That's relatively easy to do, and there are tables that convert t-values to p-values and other values to p-values as well. They're easy to find. All you have to do is take the t-value and find the corresponding p-value. And once you do that, then you can decide, is it significant or is it not significant? Psychologists have chosen.
And if you are doing a t-test in any sort of statistical software package, it will give you the p at the same time it gives you the t. So you don't have to use a table or anything like that.
A cutoff point. For us, the cutoff point is p equals 0.05. To understand the meaning of that point, you need to understand what the p-value actually represents. The p-value represents the likelihood of finding that difference if, in fact, there were no real differences. If it was just by chance and you measured two groups randomly, how often would you find a difference that was that big? How often would you find that the variance between was bigger than the variance within to that extent? We've chosen 1 in 20, or 0.05, as our cutoff point. Now, we know that's not perfect, and we know it's a bit arbitrary. Maybe something that would only happen once every 19 times would still be interesting, and we account for that. And something that would only happen once every 10,000 times is clearly much more interesting to people. But it's still a point, and we had to pick one, so we went for p equals 0.05. If then, having calculated the means, and the t-value, and the p-value, you then find that there's a reasonable difference between the heights of the men and the women, that that p-value is smaller than 0.05, at that point as a psychologist you would say, we've concluded that in this study, at least, the men were taller than the women. Let's try another one. Do students...
And that caveat he was just saying is so important, that in this study, right, given these people under these circumstances that we measured, scientists and psychologists in general have sort of like a knee-jerk reaction to be like, oh, I found this really amazing result. It applies to everyone and everything. And that might not be the case, right? And so it's important to keep in mind the limitations of which you should like apply this, right? If you do this study in America and you've got average heights of men and women, and then you do this study in like Japan, right? You will get totally different, you'll probably get similar results, but totally different means, right? Because Americans just happen to be taller in general.
Study more, do better at exams. This time we have to calculate a different statistic because we're not trying to figure out if the differences are bigger between the groups than within the groups. This time we're trying to figure out if variables co-vary, if they travel together, if an increase in one corresponds to an increase in the other, or if by contrast an increase in one corresponds to a decrease in the other. In this, we're assuming that an increase in one corresponds to an increase in the other, that studying and getting good exam grades go together. And we can see the relationship graphically. But to calculate it, we need to calculate what we call the Pearson's R. This formula that I've shown is a bit of a simplified...
And Pearson's R is the statistic you use to mathematically look at the correlation.
Formula for it. It's simplified specifically in that we're assuming that we're using populations rather than samples. but that's fine because it still gives the measure, or still gives the overall idea of what it is that we're doing. We're measuring the covariance at the top. That's the covariance of x and y, x being one variable and the other variable, let's say studying and exam grades. And underneath them, we have the standard deviations of x and y, the way that they deviate from their particular means. So what we're looking at again is the variance between them. We're looking at how much they vary together, and the variance within them, how much they vary individually, whether they just vary. And if that white noise at the bottom is bigger than the covariance at the top, we say it's not a meaningful relationship. But if the covariance at the top is bigger than the white noise at the bottom, then we say it is a meaningful relationship. And again, as with the t-value, you need to then translate that r-score into a p-score. And if that p-score is less than 0.05, you can say this is a meaningful relationship. Furthermore, if you have an r-score, the bigger the r-score, the stronger you know the correlation is. Correlations can only vary between 1 and -1. 0 meaning no correlation at all, 1 meaning a perfect positive correlation, meaning that as one goes up, the other one goes up exactly as it goes up, and -1 being a perfect negative correlation. As one goes up, the other goes down in exactly the same kind of way. So that's how you calculate whether or not one variable is related to another variable. The other two questions, I'm not going to go into the specific statistics of them, because these statistics get a bit longer and much more complicated. But it's the same basic idea. You measure the variance that happens between, and you divide it by the variance that happens within. And if you want to calculate a regression weight, you're looking at whether exercise, for example, predicts exam results.
And so here again, it's a slightly more complex formula you're using, but it is the same principle as he's saying, where you would essentially apply a correlation framework to how these various variables work together.
Then you specifically look at the weight, the regression weight of one variable predicting the other. You look at the p-value, you decide if it's significant, and then you look at what we'd call the beta to decide how strong that relationship is. For the other,
And the beta can be interpreted. So there's a standardized beta and an unstandardized beta, and one can be interpreted like a T and one can be interpreted like an R, and I'm blanking on which is which, basically. But essentially you can kind of look at it in the same way that you would look at a correlation coefficient, that Pearson's correlation coefficient.
other one, the much more complicated question, how do exercise and parties together predict exam results, in which one could be going up and the other could be going down and they could be interacting? We have to do an analysis of variance, which is insanely more complicated but adds up to more or less the same thing. And this will allow us to see whether both have positive effects, whether both have negative effects, whether one only has a positive effect when the other one isn't taken into account. That's what we call an interaction. This gets really interesting, and for us it's kind of exciting. And this is how statistics help us figure out any number of variables.
So just like regression is a more complex version of correlation, and ANOVA is a more complex version of a t-test, essentially.
Another way that I won't even put up on a slide because it's much more complicated, it's called structural equation modeling. We can simultaneously calculate the relationships between many different variables at once. You can have tens or hundreds, if you're particularly crazy, of variables in one particular equation. You put them all together, you could see, does this predict that while that one is predicting this? We think that's cool. Hopefully you do too. But it's the way that you can figure out whether exercise...
I love that. It's so true, because psychologists are like, this is so cool, and probably other people are like, why? Right? So SEM I used for my master's thesis. And there are programs where you basically kind of write the equations. The program I used, I really loved because you put your data into it, and then you could actually draw the relationships you wanted to test, and it would create the formulas for you based on the picture you created. It's amazing.
And studying and partying and drinking and the number of friends that you have all predict your exam results. And whether exam results and the ownership of a car and the number of parties you go to and the amount that you exercise predict how happy you feel. And you can do that all at once using this one particularly large set of equations. So that's really fun. So the take-home message for statistics is, if you have a question and if you have data, then we have a formula that can help you answer that question using that data. Statistics can be difficult, they can be confusing, and they can be complicated. But statistics allow us to measure the relationships between multiple variables to decide whether or not those relationships are real or illusory, and to to decide how strong or how important those relationships are. And with that,
So I love that because he just explains everything in such a good way. I'm gonna look real quick to see if I can find a good structural equation model just to give you an example of the types of things you can look at with this. And the really interesting thing is that social scientists have had to come up with these methods to test things because we ask more complex questions than people might do in the natural sciences or even in mathematics sometimes. So a lot of these methods like structural equation modeling, like the process method, that's a new way of looking at regressions, like hierarchical linear modeling, all these advanced stats techniques are usually developed by psychologists rather than statisticians, which is really interesting. But this will just give you a couple different ideas. So this one looked at intelligence related to academic performance. Looks like they gave an intelligence test that had 4 different scales and then looked at a couple different things for academic performance. It can get pretty complicated where you're looking at things like how do like your parents' level of depression or even your teacher's level of depression, right, influence you. Sometimes it can be a little more simple where we might just be looking at things like blood alcohol and the environment and aggression. And then again, it can get much more complex where you're using lots of different variables to predict one variable. And this is about like sexual involvement and sexual behavior. And so if you're interested, you can just sort of like scroll through these and see all the complex questions you can ask with structural equation modeling. And again, once you know how to run it in a stats program, it actually isn't that hard to do and really rewarding because you can ask and answer much more complex questions than you can with just a correlation, for example, although this is also based on a correlational methodology. Alrighty, so we'll stop there for today. Thanks for hanging in. And next week, we're going to talk a little more about numbers, a little more about some of the more advanced stuff. But I think that hopefully I'm making it approachable. That's my goal in this, is to always make it not overwhelming, to just sort of give context for these things. So have a great weekend. If anyone's going to be at homecoming tomorrow, I'll be there with my kiddo. If anyone wants to meet her, just look on the bounce houses, that's where she'll be. And have a great day.